Next speaker is just this second arrived from York. Is Ed Corrigan, who we all know well, from York, and he's going to talk about classical and quantum aspects of integrable shocks.
Well, first of all, thank you very much for inviting me to talk about something which is completely disconnected from the meeting. Well, sorry about that. And if I'm also disconnected from the meeting, it's because the traffic from York is absolutely horrendous today. It's a very beautiful example of compression waves almost all the way between here and York. Fantastic phenomenon. But I'm not going to talk about that. What I want to talk about is something that I've been thinking about for some years with Peter Bocock and Christina Zambon, who was originally my student in York and is now a postdoc. But we've continued working together, and I want to talk about what we've been thinking about. It occurred to us a few years ago to ask a question, and then it turned out that the question, of course, had been asked by other people before. But anyway, it occurred to us to ask the question, what sort of situation can you think about in quantum field theory, or classical field theory for that matter, where you have a shock, so simply a discontinuity. Now, there's quite a big history, of course, on the study of defects in classical systems or in quantum systems, but we wanted to think in terms of a shock. And the simplest example of a shock is a hydraulic jump or a bore, and the thing that you have to bear in mind about a shock is that there is a field discontinuity. So in this case, the field is simply the velocity, and in an ideal situation, you have a jump which takes place over a very short period in space, very short distance, and a jump between one velocity and the next. And of course, there are nice, continuous, smooth equations which model the development of a shock. An example is Berger's equation. And then, of course, another example of the same sort of thing is where you have a sudden jump in the speed of a fluid, or from supersonic to subsonic. That's a similar kind of thing. Or you could have a dislocation following an earthquake or something of that nature, where the position field, so the field tells you where the material is, has a discontinuity. And of course, in solid state physics, there are many kinds of impurities that occur, and I'm not going to list those. But the important thing to remember that in each case there's some physical quantity which is discontinuous, and then there are other physical quantities which remain continuous. So for the shock, for example, the velocity is clearly discontinuous, but you don't lose any fluid anywhere, so in a sense you have a conservation law of momentum, basically. So that's the idea. And then the question is, can we think about this in the context of an integrable system, like Sine-Gordon or KdV or whatever? Does it make sense to have this kind of discontinuity? Now, basically, I'm going to talk about the work that we have done, and the papers which have red spots are the ones which are probably the most relevant to what I'm going to say. But as with everything, one is never the first person to think about things, and it turns out, of course, that Delfino, Musado, and Simonetti in 1994 really stimulated this kind of investigation, although when we started, we didn't have this paper in mind. And then a little bit later, Connick and Leclerc did a very nice piece of work which is entirely relevant to what I'll say later on. But again, the motivation was somewhat different to ours. And then there's another approach to the whole story, which I won't talk about, by Mintchev, Ragusi, and Sorba, where they sort of changed the rules a bit to the ones that I will discuss later on. And there are a couple of more recent papers which are developing the same sort of theme. One by Vincent Caudrelier, who was in York and is now in City University, and another by Habibul and Kundu. So what's the idea? Well, being a simple-minded sort of person, I have to think in simple-minded kind of ways. So the basic idea is simply to have a kind of junction between two field theories. They could be the same on either side, and typically we'll think of this junction as a discontinuity. So what we would expect to be able to do is to write ourselves some kind of Lagrangian for the fields on either side, together with a contribution which would only be effective at this point. So we'll have some contribution which has to be effective exactly there. And of course that could depend on, in principle, it could depend on the fields on either side evaluated at this point, or their time derivatives, space derivatives, or whatever you like. But the nature of the game is to ask the question, what kind of constraints would you have to put on this functional of u and v and their derivatives, such that if the field theories on either side were integrable, then you didn't destroy the integrability. So it's a sort of mathematical question, really. It's not motivated by any specific piece of physics. So let me give you an example, which is perhaps the simplest example to think about. If you have free fields on either side, so they're simply Klein-Gordon type fields, there they are, on either side, and then you take your boundary condition to this unlikely looking combination, then you find, just the standard Euler-Lagrangian trickery, that u and v have to match at the boundary, so the fields are actually continuous there, but their first derivatives are discontinuous. So there's a gap in the first derivatives which is proportional to the common value at that point. And that's just a typical delta impurity, where you have a continuity in the fields but a discontinuity in the derivatives. So if you think about the Schrödinger equation, for example, that's exactly what you would have if you put in a delta function potential. Now, a typical aspect of this is that if u and v are not free fields, then of course you can put in a delta impurity if you like, and of course people have done this. In fact, many people have done it, and typically you have to consider what happens numerically, and because the integrability is typically destroyed. So for Sine-Gordon, there's quite a lot of investigations, and for nonlinear Schrödinger, similarly KdV and so on. And this bunch of people have done quite a lot of work actually, but I mention them only in the context of Sine-Gordon. So typically a delta impurity has transmission, reflection and bound states. So the spectrum is slightly enhanced if lambda is negative, and there will be transmission and reflection. If you send a wave in, you get a bit coming back and a bit transmitted. So that's a typical thing, and typically it's not integrable. So this kind of thing is not what we're interested in. Let me give you another example, which of course is not supposed to be obvious. I'm just telling you the answer. Let's suppose instead you were to take B to have this sort of form. So it's first order in time derivatives, so you've clearly violated time reversal, together with a function which just depends on u and v and none of the other derivatives. Then, if you pick this function this way, you find that the various equations are the Sine-Gordon on the left or the right, together with a pair of boundary conditions, or defect conditions, or shock conditions, depending on what you want, what language you want to use. Now, the thing is that this is absolutely different to the delta impurity. It is integrable, but that I'm not going to show you because I don't have so much time. But the point is that you can construct sort of lax pairs, or you can investigate conserved quantities, and you can check that actually you haven't lost integrability. Another interesting thing is that this is a kind of frozen Beckmann transformation. If it wasn't at one point x0, and if I allowed the x derivatives to be entirely free, then eliminating v or u gives the Sine-Gordon for the other equation, and that's the typical Beckmann transformation for the Sine-Gordon. Now, of course, this wasn't just pulled out of the air. What we did with Peter Bocock and Christina Zambon was to allow this to be quite general, and then we looked at conserved quantities. So the spin 3 or spin 5 or whatever conserved quantities demanded that they remain conserved, and discovered that this was the possibility that did the job. But I'm not going to explain that story for you because it's a little bit involved. Typically, also, there's no reason why U and V should be continuous. And therefore, that's why we say that this is more like a shock than a typical delta function impurity. There's an interesting thing you can do, which we did right at the very beginning. You can look at the energy, which of course you'd expect to be conserved with this extra piece added, because you haven't broken time translation invariance, so energy is automatically preserved. But an interesting feature is that actually momentum can be exchanged just as energy can with this kind of shock. So there's something going on there which we don't specify except by the shock conditions. But whatever's going on allows you to exchange both energy and momentum with the shock. And to see that, it's quite instructive actually, so I'll just run through it quickly. If you look at what you might think the total momentum should be on either side, so that's the total momentum, and then you look at how it changes with time, then obviously it's not going to be conserved because U and V don't match at the boundary. Instead you have boundary conditions of this type. And so when you put these boundary conditions into this discontinuity in P dot, what you find is that P dot looks like this. And now you see that that can be the time derivative of a functional of U and V, provided these sort themselves out to be a total time derivative and these actually cancel. So there are two conditions which you require, and then this will be d by dt of something which is just a functional of U and V. Clearly, in order for that to work, you need a sort of integrability condition for the first bit, which is just a wave equation for d. So d must be a function of u plus v or u minus v or both. And then this nonlinear relation, which relates the shock potential d to the potentials on either side, which could be different. For the sine-Gordon, they're the same. And now for sine-Gordon, you can go back and you can see that this precisely gives the answer that I told you before. So the shock conditions allow this exchange of momentum as well as energy with the whatever this discontinuity is. You can use the same trickery, of course, in other situations. So you could have collections of free fields on either side. You can relate Liouville to Liouville, or you can relate Liouville to free, because there's a Beckmann transformation that does that. And there are various affine Toda field theories that you can play with in this way. So there's a number of possibilities. And as I said and emphasize, you can actually go through the process of checking the integrability in various ways, and we did that. So we're happy with that, and it seems to be okay. Now, an interesting thing is that, let's look at the quadratic limit first. So if we just take the quadratic limit, so we replace the cosines by the lowest order pieces, then it's a matter of a little exercise to show that this is actually a purely transmitting shock. So if you send a wave in, it comes out the other side, but it's delayed. So there's a change of phase, but there's no reflection. And similarly, there's no bound state associated with this. So that emphasizes again that it's quite different to a delta function impurity. Of course, we can elaborate a little bit, because we could have several defects at different places, because the conditions are entirely local. So we can have any number of them that we like. And in fact, although I probably won't ever get to talk about it, we can even make them move. There's no reason why they shouldn't move around and indeed scatter with each other. So it's an interesting sort of object. Now again, let's continue in this simple-minded way and think about the solitons in sine-Gordon, which of course Skyrm regarded as a sort of primitive model of hadrons in the 60s. It was very stimulating for all of this business. Now let's suppose, I'm going to abbreviate this a bit, but let's suppose we have a soliton coming in on the left. So this is a typical soliton where the capital E is just the exponential of some linear function of x and t. And of course, A and B contain the, basically tell you what the velocity of the soliton is in terms of its rapidity theta. So that's a typical soliton. A typical anti-soliton would just interchange the plus with the minus. So the anti-soliton just interchanges the numerator and the denominator. An outgoing soliton, well, of course, it's not so obvious that what will happen is that an incoming soliton goes out as a soliton, but in fact it does. That's the only way you can satisfy the boundary conditions, except that the outgoing soliton will have some phase attached to it, which is additional. And now you see you can compute that phase, and I've done it for you here. The parameter in the shock condition I called sigma before, but let's say that sigma is e to the minus eta, and then you find that this change of phase is the hyperbolic cotangent of eta minus theta over 2. Now, some people have said to me, well, you know, these things are just really like solitons somehow, and therefore it's not surprising that a soliton scattering from this will behave this way. But actually it's not quite right, because if this was a soliton, so just pretend for a moment it was a soliton also of rapidity eta, then its scattering with the other soliton coming in would cause a change of phase which is exactly the square of this. That's a well-known fact which was again figured out in the 60s. So the change of phase if a soliton meets another one is actually the square of this, not this itself. And the important point about the square is, of course, that it's always positive. For real rapidities, this is always positive if we have z squared. However, we don't have z squared. We have z. And that means that sometimes this can be negative. And then this is a very important point, because if it's negative, what comes out is actually an anti-soliton, not a soliton. So this device is able to either preserve a soliton, can just go through with some change of phase, or you can flip to an anti-soliton as you go through and you get a different object coming out. And of course, if eta and theta happen to agree, so if the soliton coming in has just the right rapidity tuned to this parameter, then of course this diverges, in which case there's an infinite delay and the soliton never comes out at all. It's simply eaten. And you might say, well, that doesn't make any sense, but the answer is it does, because the energy and momentum of that soliton have been captured by the shock condition. So it's just sitting there, hidden in the shock. So to summarize that, it's quite useful to remember that if eta is negative, then z will always be negative, so the soliton will always emerge as an anti-soliton. And in effect, the defect, the shock, gains 2 units of topological charge, so you sort of charge it up. On the other hand, if the eta is positive and theta is less than eta, then z is positive, so the soliton comes out as a soliton, but it will be delayed. No change in topological charge. If theta equals eta, then I said the delay is infinite, so actually the soliton simply disappears, but its energy and momentum has not vanished. It's still there. And then finally, if theta is greater than eta, you find that z is less than 0, and again the soliton emerges as an anti-soliton again. Incidentally, you might wonder about this. You might say, well, okay, well, let's suppose we started with a situation where the soliton had already been eaten. So we start with a jump. Is that stable? Will it decay? And the answer is that classically it will not decay because there's no feature in the system which tells you what time it will decay. So in other words, if you're going to treat this in a reasonable sort of manner, you do need some kind of quantum mechanics in order to give you the probability of decay within a given time. So we should see this state coming back somehow. If we can look into the quantum field theory, we should see this state coming back in an interesting way. And indeed we do. So just in case you think it can't happen, this is what it looks like. A soliton can come in and then go out as an anti-soliton, leaving a jump behind. And that's a perfectly good solution to the setup that we have described. The energy is perfectly finite, and there's no loss of energy and momentum here. And because the defect conditions have a periodicity 4 pi, then in fact there's no energy stored here. But if the soliton is eaten, then the jump will be 2 pi, and then the energy will be stored, along with the momentum. So it's an interesting kind of thing. This boundary condition, in some sense, looks like a soliton, but it's not a soliton because it behaves differently with respect to scattering the other objects. So in a sense, it's a new sort of object. Of course, we can be more elaborate if we wish. We can have multi-solitons coming along, and they will each scatter from the shock and collect an extra phase, but not more than one component can ever be eaten. That's necessary for consistency because of the periodicity with respect to 4 pi, but also it's a fact because the rapidities must be different for a multi-soliton solution. You cannot have solitons with identical rapidities. It's just not allowed. So that's perfectly consistent. Several defects you can have, and they will act independently on a passing soliton. So you can check this for a few, and you become convinced, so that the total delay is just the product of the individual delays. And I've already said that the difference between an oddly charged defect and an evenly charged defect is exactly the energy that a soliton would have of rapidity eta, and similarly for the momentum. One interesting feature which we've wondered about is the fact that since we can turn solitons to anti-solitons and eat them, actually we could perhaps use this device, if we could ever manufacture one, to control solitons. Why not? We could control them, and then we could construct devices. Now, unfortunately, I cannot pull out of my pocket a system where this actually works, but I can show you how you would build a gate. If you wanted to play with solitons, then you could imagine doing some kind of computation with solitons, and as long as you can make what's known as a Toffoli 3-bit gate, then you can construct all other logic gates by putting them together in various combinations. And you see it'd be rather simple to do this. The idea is that a 1 is represented by a soliton, and a 0 is represented by an anti-soliton. And so what you really want is that when 2 solitons pass, the next one must flip. And that's a Toffoli gate, whereas if 2 anti-solitons pass, nothing happens. So if you look carefully, that's what goes on. And it's actually rather easy to arrange that, provided you could imagine that the defect parameter changes a little bit as a soliton goes by, but remains the same as an anti-soliton goes by. And then if 2 solitons go by, it climbs up enough so that the next soliton is flipped to an anti-soliton. You see, it's very simple. If you could arrange it to happen, then that's probably how you would try to do it. So it's just a pure speculation and a cute little thing that we could, if we wished, use these devices to compute. But first of all, we have to find a way to make them, of course, and that we don't know how to do. In case you've forgotten, the Toffoli gate does that in terms of the standard XOR and all other gates can be constructed by combining these. Anyway, that's a kind of interlude. All right, so I've told you a little bit about the setup, the question we asked, and I've given you an example in Sine-Gordon. And now I want to say a little bit about the quantum properties. And this harks back a little bit to what Delfino, Musardo and Simonetti had to say, and also Koenig and Leclerc. So let's think about the quantum properties of this Sine-Gordon shock or jump. What do we expect? Well, what we would expect is that there's pure transmission. Why would we expect that? Well, that's what we get in the quadratic limit. A soliton going through just collects a phase factor. So what we would expect is that if everything worked as nicely as we hope, then this is just a question of pure transmission. There's no reflection. And the pure transmission should be compatible with the already known Zamolodchikov bulk S matrix. And then what else would we expect? Well, if we imagine that the ground state, so that the parameter eta or sigma is chosen so that the ground state corresponds to no jump at all, then all the even jumps have the same energy and momentum, and we would probably expect that this would be a unitary S matrix or transmission matrix which describes the transmission of a soliton or an antisoliton through the defect. On the other hand, the odd one, we would probably expect that that is peculiar in some way, and in fact it turns out not to be unitary at all. And the reason is quite interesting, because the situation where a soliton is eaten, which corresponds to a particular rapidity, turns up as a complex pole, so it becomes a resonance or an unstable bound state in this setup. And then when you work out the transmission factor corresponding to it, that ends up not being unitary, because it's describing something which will eventually decay. So that sort of comes out in the wash. I won't give you all the details, but that sort of comes out. So how are we labeling this? Well, the alphas and the betas run over either the even or the odd integers, depending on whether the defect is even or odd. So these are all the even integers, these are all the odd integers. And the A and the B run over the soliton labels, so you can think of those as being plus or minus 1 if you want, for the soliton and the antisoliton. So, as I say, it's supposed to be compatible with the bulk S matrix. And the bulk S matrix is a known thing, which maybe I won't remind you of. But anyway, it's a known thing. And what I mean by compatibility is simply this set of triangle relations. So you have to imagine that if we have two solitons meeting our defect, which is represented in black here, so they meet the shock, then just by organizing how they start off, which could be a very long way off, they would ultimately, since they have different rapidities, either scatter before they meet the defect or subsequently to meeting the defect. And the idea is that those should be the same. And that's the compatibility relation which was assumed by Delfino, Musardo and Simonetti. But it's a little bit different to the relations that the other people, Minchev et al., assume later on. But anyway, this seems to us to be a sensible thing to assume. So in detail, the equations you have to solve are like this, and you're given the S matrix, and therefore you ought to be able to solve the quadratic relations for the transmission factors. These are infinite dimensional matrices, but one interesting thing is that the even and the odd never mix. So there should be two solutions, one corresponding to the even integers and one corresponding to the odd integers. At least two solutions, because of course there could be more. Now, as it happens, you can go through the business of writing down all the recurrence relations that must be satisfied by the entries, and we did all that. But in the end, what you find is that the solution you get is exactly the one that Connick and Leclerc found in 1999. They were thinking about something different, but in the end, they found exactly the same solution, because it is, in fact, essentially unique, apart from the even and the odd never mixing and then therefore being separate. They didn't worry about that, but actually it's quite important that they don't mix up and that they remain separate. So the Connick and Leclerc type solution is quite an interesting thing, but you can easily work it out by writing down all the recurrence relations and just seeing what you get. So the technicality is a little bit tricky, but in the end the answer looks like this. So there's a free parameter which in a way you can just remove by a clever change of basis subsequently. But the important parameters are this Q, which contains the information that has the coupling constant in it. So if I was to tell you about Zamolodchikov's S matrix, the Q, there's a little q, which is e to the I pi gamma, and gamma is 8 pi over beta squared minus 1. So that's how the coupling constant comes in the Sine-Gordon model, and the rapidity comes in via these factors, which also involve the rapidity and the coupling. So I call those x. So anyway, q squared is minus little q, or if you prefer, q is just that combination involving the coupling constant. So it's a non-perturbative thing, actually. You won't see this in perturbation theory. And then the other parameters that appear, well, the way I've written it, of course, is supposed to be very suggestive that this eta is actually the same eta as we had before, although, of course, you can't assume that because it could be slightly different, but it comes in this way, and it's useful to parameterize the extra constant in that way. And we would not like to argue that this is surely close to what we had right at the very beginning. Now, this overall factor has to be determined by some assumptions which involve unitarity or crossing or some set of arguments, and the arguments that we used were the fact that for the even ones, T was unitary, and if you annihilate a soliton and an anti-soliton, then you know what happens, basically. You just get the vacuum, and that gives you a constraint on this function. But still F is not determined uniquely. And one interesting thing is that these relations, if you try to apply them to both of the even and the odd solutions, you cannot do it. You cannot do it simultaneously to both sorts of solutions, which is an intriguing thing, but it fits in very nicely with the interpretation I'm going to make. But anyway, Connick and Leclerc did the job for us, and they suggested the sort of minimal function like that, although actually there are other solutions as well where you can multiply these by the so-called CDD type factors. And this function looks a little bit complicated, but its precise feature doesn't really matter. It looks as though it's got a pole here, but actually that pole is cancelled off by a pole in R bar. So there isn't actually a pole at that particular place. But there is a pole at other places, but we'll come to that in a minute. Now then, let's make a few remarks. The off-diagonal elements contain this, according to my parameterization. And you can see that when eta is negative, those are going to dominate. And therefore, when eta is negative, a topological charge changing by 2 is dominant. And that sort of corresponds to the classical picture that if eta is negative, a soliton will always turn to an anti-soliton. So we would expect these to dominate in the quantum field theory. But on the other hand, when eta is greater than 0, but theta is less than eta, then the diagonal elements still dominate. But if theta is greater than eta, the if theta is less than eta, the diagonal elements dominate, but theta greater than eta, the off-diagonal elements dominate. And again, that fits with the classical sort of picture. It doesn't tell you that eta is exactly the classical parameter, but it tells you that the shape is perfectly consistent with what we would have expected on the basis of our classical arguments. Now then, theta equals eta is not special. There's no particular pole at theta equals eta, which is the place where the soliton can be eaten, but there is a nearby pole, and the nearby pole is here. And as beta goes to 0, 1 over gamma goes to 0, so this tends to theta equals eta. So this pole looks as though it's a sort of perturbation of the curious Eaton state in the classical model. If we work out the energy of this state, then you see that its energy's got an imaginary part, and the imaginary part has the right sign to indicate a state which is unstable, and the width of the state is proportional to sine pi over 2 gamma, and clearly that goes to 0 as beta goes to 0. So the thing becomes stable as beta goes to 0, which is the classical limit, but is otherwise unstable. And we can use this state, if you like, as a bootstrap to construct the odd transmission factor, and then you find that the odd transmission factor is not unitary. So it all sort of hangs together, even though I can't give you the details. Of course, if we wanted to make some definitive statement about how the constant eta is connected to the classical theory, then one way to do it would be to think about objects that you can calculate perturbatively, or objects that you can calculate in some other way, maybe using TBA, maybe using some other well-known technique. But since I quite like perturbation theory, and have played with that many times before, you might start to look at the breathers, because you know a soliton antisoliton can make a bound state. That was one of the things that Skirm found very intriguing about the model in the 60s. You can make a bound state, and the bound states occur at these values of the relative rapidity of the soliton and the antisoliton. And then you can use a bootstrap principle to work out the transmission factors for the breathers themselves. And what you find for the lightest breather is there's a lot of cancellation that goes on, everything sort of sorts itself out, and you find just a very simple function for the lightest breather. And actually this formula is precisely what you would get if you looked at the linearized version of the Sine-Gordon, and you did the little exercise that I gave you right at the very beginning to prove that you had pure transmission and nothing else. Well, the factor you would work out is exactly this. So I'm not saying that eta is precisely the same, and it remains to be seen in perturbation theory, but at least the form of the thing is exactly the same as what you would get from the bootstrap and the classical computation. So that's a starting point for looking at the story perturbatively. Now there are other things that one can check. For example, I mentioned that the diagonal elements have a dependence on the coupling constant which is not perturbative. Well, actually you can get at that dependence using a functional integral argument, and we put that in our paper. And indeed there's a difference between solitons and antisolitons, and that also comes out in the wash. Now, since I'm running out of time, let me just finish with some questions. As I mentioned at the beginning, we can actually make these defects themselves move and scatter. Peter Bocock quite likes the fact that the the shock conditions are like Beckland transformations, and if you've got two scattering shocks, they will come in the opposite order, and then the compatibility with soliton scattering is like Bianchi's theorem of permutability. So it sort of fits in with the thing that Bianchi liked more than a century ago. And the question is whether this idea extends to quantum field theory. So can you construct a scattering matrix for these shocks themselves? And the answer is, well, we've proposed a scattering matrix for these objects, but we're not quite sure that we've got the right answer. It's not a quite trivial thing, you see, because the classical scattering of these things is entirely trivial. They don't affect each other. In fact, they can just sit there doing nothing. They're a little bit like BPS states that can just sit there not interacting. And they're entirely happy to do that classically. So that means that their scattering is going to be a quantum effect if it exists at all. So it's not something that you're going to get at rather easily, but you can do it by a kind of compatibility argument of the type that I mentioned before. However, we're not clear, although we've made a proposal, we're not clear that the proposal is really right. Then a question, of course, is do these objects have an alternative field theoretic description? In other words, what are they? Can we think about them in some other way? In other field theories, we can play the same sort of game, and I mentioned that there's a group of people who've been looking at supersymmetric versions, where things change a little bit more dramatically than they do if you just start looking at field theories with more components, such as affine Toda or nonlinear Schrödinger, KdV, MKdV, and all that sort of thing. And then finally, a challenge. Beckland transformations seem to be quite basic objects, because after all, they were invented by Beckland for purely geometrical reasons more than a century ago. And then they were resuscitated by applied mathematicians in the 60s as a device for generating solitons. And then here they turn up in a sort of unexpected way as possible shock conditions which maintain integrability. But the question is, can one construct or can one visualize or construct a physical situation in which they're realized quite naturally? And I've hunted around in the literature, but I haven't found such a thing. But if we can find such a thing, then it might be technologically useful for the reasons I mentioned before. Anyway, I'm sorry to have gone on, but I hope you get some flavor of what we've been trying to do. I realize it's got nothing whatever to do with string theory, so I apologize for that. But maybe it's interesting anyway, and you never know how things come around in the future. So thank you very much for your attention.
Two of your defects, is there any way that the total amplitude for scattering a soliton through them would match the Sine-Jordan symmetry? Any way your defect?
Well, we didn't look at that, but actually, if you have, it's true that if you have two of these things with the same parameter, then in some sense they act classically like a soliton. So they're like the ingredients for a soliton. So they're sort of like quarks sitting inside the soliton, and if you scatter another soliton through them, then, of course, if it's flipped by the first, it'll be flipped back by the second, and so on. And the scattering is exactly the right thing, as though it was a soliton. So, in other words, two of these things are like an alternative description of a soliton. But what we haven't checked is your question as to whether Zamolodchikov's S matrix is exactly the product of two of these T things. At first sight, it doesn't look like that because the T things are sort of infinitely big. But maybe that's just a confusion.
But also in the scattering of a soliton with an anti-soliton, you have reflection. But in these defects, you don't have reflection, only transmission. So it cannot be.
Any other questions?
Well, yeah, okay, we can talk about that after.